A sphere is dropped, striking water at 4 meters per second. We see the shark fin indicating that this is water, so I didn't really have to explain that it's water. It hits, scaring the shark away, and descends 10 meters before it comes to rest. We assume this is a sphere of ice so that its buoyant force is very nearly equal to the gravitational force. Buoyant force being slightly greater, but won't significantly affect our results. And even more significantly, we're assuming that acceleration is constant, which is completely not the case. And we use m for the mass because no mass was provided. Okay, so we use the impulse momentum theorem. F net delta t equals delta p, which is m delta v because the mass is presumably constant. There'll be a little melting, but not much. We know m then, and we can easily find the delta v. It's from 4 meters per second to 0. That's negative 4 meters per second. And we want to find F net. Well, if we know m and delta v, what do we need in order to find F net? Well, we need delta t. Now, this is something that we kind of get used to when we use the impulse momentum theorem, you know, the four quantities that are involved and how they're related. In any case, we want to find the delta t. So we're going to use the fact or the assumption that acceleration is uniform, so that delta t is just your displacement over average velocity. Now, this is the case because acceleration is constant. And also then by the definition of average velocity as displacement divided by time interval, if you want to be more specific, and I usually do. Okay, so the division is very simple. The average velocity, if we're going from 4 meters per second to 0 with uniform acceleration, that means our v versus t graph is linear, meaning on any interval, the average velocity for that interval will be the average of the velocity at the beginning and at the end of the interval. So the two velocities are clearly then 4 meters per second and 0. So that our average velocity is the mean of those 2 meters per second. Divided into the 10 centimeter displacement, we easily find that the time interval is 0.05 seconds. And then, using the impulse momentum theorem, we can divide both sides by delta t and get our F net, knowing, well, in terms of the mass m, because we aren't given a mass m, but we do easily find delta t to be negative 40 centimeters per second and delta t to be 0.05 seconds. From this, we find that F net is m times negative 80 meters per second squared. Now, from this we can infer that the acceleration is negative 80 meters per second squared, since the net force is equal to the mass times the acceleration. And of course, we could assume uniform acceleration for an object slowing from 4 meters per second to 0 over 10 centimeter displacement. And we can again easily find the acceleration. But the point of this calculation is that we never needed to find the acceleration. We just applied the impulse momentum theorem. And if you remember where the impulse momentum theorem came from, it's not surprising that we can bypass the acceleration, because to get the impulse momentum theorem for constant forces, we just substituted acceleration equals F net over m into basically the definition of average velocity. Final velocity is initial velocity plus acceleration times your delta t. Plug that in and we immediately get the impulse momentum theorem. So acceleration is kind of pivotal, but you understand that that derivation bypassed the calculation of acceleration and allows us to calculate F net just from this information.